In this first lecture, we are going to start by taking a look at the Atmega 328P microcontroller, which is the microcontroller that we will be using for the duration of this course. In the previous subject, Embedded Systems 1, you worked with the 8031 or 8051 microcontroller. And that family. Here we are going to turn our attention to the Atmega, which is part of the AVR family of controllers. And we're just going to start by taking a look at this controller and just the basics of it. We're not going to go very deep into the architecture of this controller, but we will focus a lot on how we use this controller. So what we want to do here is just to get you up to speed with this Atmega and basically how you will be using it. And then we are going to take a look at how do you write your programs in Atmel Studio, because Atmel Studio is the compiler that we use in this subject. So in Embedded Systems 1, you used Kyle. Here you are going to use Atmel Studio. And then we are going to simulate the programs that we have written in Proteus. Now that you are familiar with, because that you have done in Embedded Systems 1. The Atmega is quite friendly in the sense that you program it directly from your computer. You do not require an external programmer because it is situated on the Arduino board. And you just plug it into the USB of your computer, and then you can perform the programming from there. But we'll get to that. So for now, let's just start with the basics. So what is the Atmega 328P? Like I mentioned, the Atmega is part of the Atmel. It's made by Atmel, and it's an AVR controller. It's an 8-bit microcontroller, and it has a very good performance. In the sense that it is rather fast and it has a lot of powerful instructions, which most of them are single clock execution. Because if you refer to the to microcontrollers in general, some of them do not execute. It takes about 1 or 2 clock cycles to fully for some instructions to execute. Whereas on this one we have where most of your instructions will execute on a single clock cycle. You have 32 8-bit general purpose registers, and you get up to 20 million instructions per second with a throughput of 20 megahertz. So we can see that it is rather it is not a slow lazy controller. But once again, we're not going to go too deep, but I'm just giving you a basic introduction into this microcontroller. We have it has nice peripheral features. You have timers and counters on this, like you did with the 8051. You have a real-time counter with a separate oscillator. There's PWM channels, which is pulse width modulation, so that is quite handy to perform, being able to perform pulse width modulation on this controller. There is 8 built-in 8 built-in 10-bit ADCs, so that you'll find on port C, which we'll get to. And then there's also a serial interface. It has built-in SPI, it has built-in I2C, which is something we're going to use a lot. We are going to work with the I2C interface, and we are going to do serial, and we are going to use the SPI. So that is all quite handy, because there's a multiple a big array of, or shall I say, collection of peripheral devices that you can that is available using these protocols, I2C and SPI. Things like external LCDs, temperature sensors, humidity sensors, barometric pressure sensors, GPSs, all of that uses some form of either SPI I2C or serial to relay the data back to the microcontroller. So which makes this really a very nice microcontroller to work with. So typically, here you can see this is the microcontroller by itself. But the way that you will receive it in the subject is it's on this Arduino board. So it's already built. It looks like this. This is part of your component packs. This is what you'll get. So let's see what this Arduino board looks like. So if we start on this side, you can see there is, so basically here is your USB cable. This is what you will connect to your computer, and that's what gives the whole board will receive its power from here, and it also receives its instructions. And if you do serial communication between the computer and your Arduino, it's also done via the USB port. Here you have some power outlets then that you can use. There's 3.3 volt, there's 5 volt ground, and you have here then also a VIN. So this is you don't have to power the board in order to make it work here. So like I said, the board receives its power from the USB. There's a built-in LED on this board that will indicate whether it has power or not. And it typically sits, I can't remember exactly where it sits now. It's one of these. Yeah, so here you've got the transmit, receive, and there's a built-in LED here that's on port B, which we'll get to. Then, if we move to, let's start with port C. So here you can see this is basically port C, and you have, this is also where the ADC basically is connected, as well as your I2C. So this SDA and SCL we know is I2C, but you also have your ADCs multiplexed on port C. So here you can see, let's just look at the jargon. This is PC0, PC1, PC2. So this is port C pin 0, port C pin 1, port C pin 2, port C pin 3, pin 4, pin 5. So here you can see we've got, this is how you know which pin is which, because here we can see it's port C pin 0. So this is also here. So you're probably wondering why is it so many things written here? In the code, sometimes you can see you'll refer to A0, A1, A2, A3, A4, A5. That will then, that's a built-in feature, so that you then know you're working with analog input 0, analog input 1, because this microcontroller has analog inputs as well as digital inputs. So you can use the analog inputs normally as you would, but when you use it as an analog input, it has the ability to obviously read like an analog signal, a different voltage, let's say between 0 and 5. You can actually then read different voltages depending on what the voltage level is. You can then get from this input, which is done by means of an ADC. So your SDA and SCL is your I2C. So if you use I2C, these two pins is dedicated specifically for I2C. Then you see here you have PC6, which you will find there, but most of the time you'll find having having access to these 5 bits is enough. We seldomly need to actually try and access more. Then if we move around here, this is a ref, which works with your the ADC system on the controller. There's a ground, and then here you've got port B. So here you can see we start from port B0 through to port B5. So we only have these 5 bits accessible on port B. That's one of the drawbacks when using this specific Arduino board. We lose some of the pins on port B, because you can see that actually here, which is used for the ISP service, which is your in-circuit programming, but we don't use this. So You could access these bits via this input if you really need to, but for most of our applications, we don't need to resolve to this. And here you'll see it's written analog. This you see is digital. What's the difference? So like I said, these pins have the capability to work with varying analog voltages. Here, this is just a digital pin. It's on or it's off. This can be used as an on or off, but it has the capability to do an analog, a varying analog voltage, whereas this can only do digital, on or off. So you'll see it has a pin number. All of them have pin numbers. So here you can see it's 8, 9, 10, 11, 12, 13. So when we define and when we start programming, you'll see you can sometimes refer to pin 8, pin 9, pin 10 instead of referring to port B pin 0, because remember the compiler doesn't know this. You'll have to go and declare it if you want to know it, but the compiler will know 8, 9 and 10, and then you should know 8 is port B pin 0, 9 is port B pin 1, just like 14 is port C0, 15 is port C1 and so forth. So this is basically a number that you can use when you want to work with a symbol or to define a symbol name that is associated with that specific pin. Then this is port B, and here you have port D. So this is port D. Now all of these are general purpose ports. You can use them for anything, but you'll notice they all have these different, all of this means it has another function as well. So here you can see we've got internal interrupts, we have our timer 1 and timer 0. So these all have multiple functions, but basically we use it for general input. But if you are going to use a timer or an interrupt, this is the pins that they are associated with. Here you can see is your pulse width modulation capability. The pins that are able to do pulse width modulation are these pins over here that's associated where you have these reddish blocks. Then you'll also see here is SCK, MISO, MOSI and SS. This is SPI. So like we said, this is I squared C. This is what when we work with SPI, we do this. Here you can see is transmit and receive. This is my normal serial. And just a quick thing you have to remember is when you program, you must make sure that nothing is connected to these two pins. So if you have a circuit that you are building or working on and you're using port D, just make sure that while you are programming, you just disconnect these two wires. Because remember, these two pins are also connected to the USB cable which goes to your computer, because the computer communicates with the board or the controller via the serial interface. And if you have something connected here, it prevents successful communication, and then you'll see your programming doesn't always want to work. So you can use this for anything. Just make sure when you program, you disconnect whatever is connected to these two pins to avoid any problems. So that is an overview of what the Arduino board basically looks like and where you will find what pins. So here you can see is also a breakdown of just this is the microcontroller all by itself with all of the pins on all of the ports, port C, port D and port B. It does not have a port A, and once again here you can see this is your USB power. You can power it separately. There is a power barrel jack. So for instance, if you don't want to power this from your computer always, there is a normal 5 volt, well 7 to 12 volt jack that you can connect a battery or anything with between this voltage. It's one of those round, it's a round barrel jack that you can then connect to the board if you want to power it in a way that's not from the USB. But that is the basics of the board. Now, the compiler that we use, as I've mentioned, is Atmel Studio, and there is a link available on Brightspace where you can click on and it will take you to the Atmel Studio website where you can download Atmel Studio. It's freeware, and you then install Atmel Studio, and that is what we use to program with and to write our programs on. but you also program your Arduino board from this platform. This is an all-in-one solution. So this is the compiler that we use, and as we progress you will see how we use it, but go and download it so long and make sure it's installed. It does take a while to download and install. It's quite a large application, so if it takes long, don't think it's something wrong. It is quite sizable, so it takes a while. Please then go and watch the video. So there is a video under all of it. So right in the beginning of all of the video lectures, there's a video and a PDF document that explains all of this, that explains the Atmel Studio setup and how to and everything you should do in order to program your Arduino. So because there's a bunch of settings you just have to do and get right. So make sure you do all of that, you get the setup working so that when you want to program, you know Atmel Studio is ready for action. And there's a full video where I explain how that is done. Now, let's go over the ports and the IOs, which is our input outputs. Now, like I mentioned, port B is an 8-bit bidirectional port, which means we can use it as an input or as an output. It has internal pull-up resistors, but you can use it for more or less anything. I use port B on mine for anything. It's like the only drawback is you don't have a full 8-bit port available on the Arduino board. So depending on your application, you can just plan around that. Then, like I mentioned, port C is a 7-bit bidirectional IO, and so there it can work as a normal port, just writing ones and zeros, but it has the capability of doing analog inputs as well, because it has an analog to digital converter on each of those pins that's multiplexed. So all of it is there, and we will get to it. Then we have port D, which is also an 8-bit bidirectional port, also internal pull-up resistors, and we also use that for anything, but make sure you just remember that you have the serial interface is on port D0 and 1, so when you program, just make sure anything connected to that serial interface is removed, and then once you've programmed it, you can connect it again. Then you've got AVCC, and AREF, which is for the ADC, and ADC7 and ADC6. That is specifically they serve as analog inputs to the analog to digital converter. But we're not gonna. Don't be too concerned about understanding all of this now. I prefer that as we work with it, you will see how it is used. Now, this is basically what the inside of the microcontroller looks like this is just a functional block diagram. So here you can see we have our AVR CPU. This is the brain, the core, all of it. And then you can see a lot of the stuff we've mentioned, you can see now is here. So here we have our SPI engine. So inside of this is all of the circuitry we require to perform if we want to use the SPI serial protocol. Then you have TWI. What is TWI? TWI is basically I squared C. What's the difference? There is no difference. I squared C is a term that is just coined by Philips, so it is basically copyrighted as a term by Philips. So if it's not a Philips manufacturer, nobody else can call it I squared C. So they call it two-wire interface, TWI, because I squared C is just two wires that we do communication on, which makes it so incredible. So there is no difference between TWI and I squared C. This is just copyrighted by Philips, whereas every other manufacturer uses the term TWI. And you can see more or less how it's connected onto the bus. We've got our data bus, and you can see this interfaces with port C, SPI interfaces with port B. You can see here you've got UZART 0, which is your serial engine. Some of these controllers have two serial engines. They've got USART 0 and USART 1, but the one we are working with only has one built-in USART, which is our universal synchronous asynchronous receiver transmitter, and that is associated with port D. Then you can see we have our analog system. We have our timers and counters, which is you have 8-bit timers and counters, 16-bit timers and counters, all of that. We have our analog to digital converters. We have our let's not talk about that. Here you can see your internal EEPROM, your oscillator circuits, and all the normal stuff that you would find on a microcontroller, like the watchdog timer, the oscillators, all of that. Flash RAM and SRAM. So, because you are familiar with these terms, because we did it in the previous subject, we will not get into the types of memory we have here, because that is something you know by now. Now, this controller uses Harvard architecture. What is Harvard architecture and how is it different from the von Neumann architecture? Basically, Harvard architecture is is quite simple. It uses separate storage and signal pathways for instructions and data. So you have an instruction bus and you have a data bus, whereas von Neumann uses program instructions and data sharing on the same memory and pathways. So it's all, so that's the difference. Harvard has separate pathways and storage sort of for your instructions and your data. They are separated, whereas von Neumann, it all uses the same pathways. So that's just the difference. So when you hear the term Harvard architecture, you know specifically associated with this microcontroller, that is where the difference comes in, or what it is when we say Harvard architecture. That is what we are referring to. Now, it's very important. In order for us to use this microcontroller, we have to understand a few things about it. As we did with the 8051, there is some special function registers that we need to understand, because these registers are very important to help us use this microcontroller, especially because it has so many functions. Because it has a built-in ADC, you must be able to switch the ADC on or off. It has I2C, which means you need to enable or disable them. It has SPI, which means we should enable or disable them when we configure them. So we need to know how we switch all of this on or off. And so that's why we're just going to take a look at some of our registers. So firstly, we are going to start with the status register, which is referred to as SREG. So SREG, and that is my AVR status register. And you can see there's a multiple different things. We are going to basically, I'm going to draw your attention to this bit 7, which is my global interrupt enable. So whenever we work with anything that has anything to do with interrupts, then you notice we are going to need to enable this, and you'll see okay, fine, we'll talk about this later, because there's applications where we use this, but we will we'll get to that. So for now, I want to bring your attention to what we use the status register for mostly in our applications here in this subject, is to enable global interrupts. Then we have the power reduction register. This is in order to either turn on or off these various different functions. So here you can see this is for 2Y interface. So if I want to use my 2Y interface, this bit in this register needs to be addressed in order to shut it down by stopping the clock to that module. So when I write a logic 1 to this bit, it basically stops the TWI. So you don't switch it on with a 1, you switch it off with a 0. And then you have your USART in order to get your USART working. So bit 1, so right here, so bit 0, this is when we want to get the ADC up and running. Here is the USART to get that up and running. Here you can see is SPI. So we have a timer here. So you can see this is how we switch on or off all these various logic blocks that we saw here in this diagram, because we can't have all of them on at the same time. The whole point of AVR is it is a low power controller, so we're saving power, but also you never have all of these devices active if we're not going to use them, because then they just sit on the bus. And so we want to only activate them when we want to use them. Now here you can see is a bit of the parallel instruction and instruction fetch and instruction executions. So if these are this is my timing diagram, and you can see here I've got my CPU clock cycle. So this is one clock cycle, another clock cycle, third and fourth clock cycle. You can see there's an instruction fetch performed here. And then here you can see my first instruction is executed in a single clock cycle. And then I do a second instruction execute, because what happens is typically while you are fetching your, you see here when the first instruction is being executed, the second instruction is already fetched, which means here my second instruction executes and it fetches the third instruction, and then so forth. So while it fetches one instruction, or while it executes an instruction that has already been fetched, it goes and it fetches the next instruction. So it sort of pipelines it. And that's how a lot of time is saved, because then there's always an instruction to execute when it's done with the previous instruction that was fetched. It can constantly keep moving. There's never dead time. So that is a very brief, quick overview of this microcontroller. Now, I know theoretically all of this is useless if it just stays there. So what we are going to do in the next session is we are going to look at writing your first program, because now we are going to see how do we combine a coding language with this hardware that we've just looked at. So make sure you go back and just familiarize yourself again with the basic architecture. And in the next lecture, we are going to write our first programs where we are going to use the IOs on the Atmega. And we will get into more detailed and more complex programs later. For now, we are going to do simple, easy things like reading switches, turning on LEDs, and so forth. And then we will progress as you become comfortable with the code as well as with the architecture. So I'll see you in the next session.